Hi, uh, thank you for joining us here on Danfoss Climate Solutions live stream. I'm Jens Andersen, and Jamie Kitchen is joining me here. Uh,
Hey,
we have a theme today which is about superheat and subcooling. And please ask as many questions as you can think up. We'll try to, or rather, Jamie will try to answer the questions as good as possible. I will just be the one directing the questions to
the
Jamie.
MC, Master of Ceremonies.
Yeah, exactly. First of all, Jamie, could you please introduce yourself?
Sure. As the thing says, my name's Jamie Kitchen, and I have been with Danfoss for a lot of years in quite a few different positions, most of them focusing around sales, technical sales, anything technical, a little bit of marketing, but mostly just um, helping people better understand, how to apply products, how products are used, as well as, a broader sense of basic troubleshooting skills, how to optimize a system, how to set it up for better energy efficiency, better reliability, things like that. Currently, I am in OEM sales, manufacturing sales, and I do a lot of technical sales across Canada, which is where I'm from. So Canada's a big country, so it keeps me busy moving from one place to another, especially now that things are opening up.
Thank you, Jamie. And my name is Jens Andersen. You might have heard some of the podcasts I've been doing. I've been with Danfoss for almost half a century, which is a lot of time, actually.
Yeah,
And,
beats me.
right now, I'm working as a senior content specialist and doing, among other things, podcasts, infographics, things like this live stream thing here. Just a question, or rather, just an information for you guys out there. Please let us know from where you are actually contacting us. We see a lot
Yeah,
of Thailand,
I see it
Belgium,
all over.
Spain, yeah, all over the world. So one from Iran, Brazil. So please let us know where you are and keep the questions coming because it's the questions that we live off. Isn't that right, Jamie?
Yes, even see Canada. Woohoo! So, it's always amazing because right now, there is a 12-hour difference between some of these places and me here right now, here in Canada at Eastern Standard Time, Eastern Savings Time. So it's amazing that, it's 9 o'clock in the morning right now and we're just, starting work. Well, other people, it's in the evening time and, they're probably getting ready to watch the news or something at night. So, that part always amazes me, especially when we're talking about superheat and subcooling.
Yeah.
I mean, it's a topic that, again, is the foundation of everything that we basically do here is based on, values of, subcooling, superheat, and of course, airflow, if you want to throw that in, are really the three traditional foundations of understanding and setting up a system to work properly. So, I'm very happy that we're actually, taking the opportunity to do this. So, where do you want to start, man? It's pretty wide.
Yeah, but Jamie, maybe we should start, take a few steps backwards and try to define what is superheat. Could you do that for us?
Yeah. Superheat, as if you've gone to a technical school or engineering school or whatever, or studied any of the textbooks, you'll probably have heard that superheat is the heating of a vapor above the point at which it changes state, which is a fancy term for saying boiling. So we know that water boils at 100 degrees Celsius, 212 degrees Fahrenheit at, an atmospheric pressure that most of us live at. Well, if you were to trap that steam, that vapor, once it's produced, in a separate line and actually add more heat to it, it would turn into a clear superheated vapor. If you want to know what a superheated vapor looks like, just look around where you are right now, because we're surrounded by superheated vapor. Nitrogen, oxygen, carbon dioxide, whatever. It is grossly superheated. And this is what it looks like. It's clear. So just about, or most vapors, once they're superheated, are clear, including refrigerants, water, you name it. So a superheated vapor is generally just heated above the point that it changes state at, and it is dry. There's no liquid left in it whatsoever.
Great. But why are we so interested in superheat? For what use is it in our context, in the refrigeration business?
Generally, a couple of things. Let's go back to, why we'd want superheat in a refrigeration or air conditioning system anyways. Superheat is added in the evaporator generally once the liquid is all gone. And we do this for one reason, and that's to protect the compressor. The compressor is designed to take a compressible fluid, which is a vapor, gases, and compress them to a higher pressure and density, or higher pressure and temperature by increasing the density. So you take a certain volume and you compress it to a smaller volume. Now, liquid, on the other hand, is what we call non-compressible. Think about hydraulics. Your hydraulic system works at, thousands of pounds per square inch. Basically, you're taking a fluid and you're pumping it at a high pressure. You're not really compressing it. So if you introduce liquid to a refrigeration compressor, generally speaking, it's going to hit that liquid and it's going to stop because it can't compress it. And unfortunately, with momentum, you're going to damage the valves. You're going to damage the pistons. If it's a scroll, generally speaking, you can survive some of that liquid. However, you still have issues with liquid refrigerant getting into the oil and diluting the oil, ruining your pump pressure, washing oil off the bearings, all other kinds of nasty stuff that you really don't want happening. Now, I call superheat a necessary evil only because it's one of those things that actually works against efficiency. We do it because we have to. So what we want to do is make sure that you minimize the amount of superheat you have. But that is kind of a fine line, because when you adjust something like a thermal expansion valve, a TXV, TXV is a mechanical adaptive metering device. Okay, it can open and close based on load. If you tune that superheat too low, you risk the chance of making the system unstable. And, not only will you have fluctuating evaporator pressures and temperatures, but you can also get liquid escaping the evaporator and making its way to the compressor, which is something you don't want. So we really want the superheat to be at, a specific range without being too high or too low. If it's too high, you waste a lot of energy. There's other negative effects that basically hit on dehumidification. We can touch on that a little bit. But if it's too low, then you risk damaging the compressor and other things that are kind of nasty. So that's kind of superheat in a nutshell.
Great. We've already got a couple of questions actually coming in. First one is Hidayat, I think it's pronounced. It's about how much superheat, or the question is how much the value of superheat for chiller and freezer application.
Okay, how much superheat, how much subcooling is probably one of the number one questions that we get, and it's completely understandable, and that's a great question. Generally speaking, there is no perfect value. What you have is a range of values, and this is why it's such a hard question to ask. In freezer applications, superheat values are generally going to be lower than in air conditioning, chillers. Probably the one with the largest range is probably residential air conditioning systems. So let's picture a system. It's always easier to picture something. Okay, take a freezer application. You might be running your evaporator at, -10, -20, -30 Celsius. You want to limit that superheat as low as possible. Why? Because the lower the evaporator temperature, the harder it is to cool the compressor. Now, keep in mind, the compressor is just about 100% cooled by that gas coming back, called the suction vapor, suction gas. So if your superheat is too high, it will be too warm to properly cool the compressor. So what ends up happening is the temperature of your discharge vapor goes up, the temperature of your windings go up, and as your winding temperature increase, the life of the insulation on those windings decreases drastically. So once again, you want that vapor temperature, that superheat, to be as low as possible. Generally speaking, on low temp applications where you're looking at, a -10, -20 evaporator temperature, -20 Celsius evaporator temperature, anywhere from 5 to 7 degrees Kelvin of superheat, 8 to 12 degrees superheat Fahrenheit of superheat is about your standard operating range. Now, keep in mind that during times of high load, your superheat is going to be higher. So if you just load a bunch of warm product in a freezer or cooler, and you drive the internal temperature of that freezer up, you're going to notice your superheat goes up dramatically. And that is a necessary evil with a TXV, because the only way for that TXV to open up is for the thermal bulb, the sensing bulb that the TXV uses to basically provide the opening force that's measuring the temperature of the suction line. That pressure has to increase inside that sensing bulb in order to overcome the forces. Okay, so picture a diaphragm in the TXV element. You have one opening force that's trying to drive the valve open. That's your sensing bulb pressure. Underneath, you have two forces, your superheat spring and your evaporator pressure. Both of those are closing forces. So if the evaporator and your superheat spring pressure are greater than the sensing bulb force or sensing bulb pressure, the valve's going to be closed. If they're equal, basically nothing's going to happen. If the sensing bulb pressure is greater, it is going to force that valve open and put more refrigerant into the evaporator. So during times of high load, you have not enough refrigerant, right, to meet the demand of the load on the evaporator initially. So what happens? Your superheat goes up. The temperature difference between the suction coming out of the vapor coming out of the evaporator and your saturation temperature increases. And this warms your sensing bulb up. This drives the valve open. Now, you can fool around with the bulb charges a bit to kind of limit this rise in superheat. But the point being is that under high load, your superheat is going to be higher. And this is standard. And as the load in the room drops, your superheat will drop with it until such time as the thermostat on the wall is satisfied. So during your operation, your superheat is going to be highest when the thermostat first comes on, and it's going to be lowest when your thermostat clicks the system off. So anytime like after defrost or when you load a bunch of product into the room, this is when your superheat is going to be highest. Now, the extreme version of this is going to be on, let's say, a residential air conditioning system. A lot of times we'll set the superheat, and I'll get back to this point, so remind me of this, factory superheat on a TXV or static superheat, these can be set quite low. So for, TXVs that we sell to manufacturers like Carrier, York, Trane, these other guys that make air conditioning systems, these valves typically open at a fairly low superheat value. Even still, let's say you have a day when it's 25 or 28 degrees Celsius outside. Great, right? It's a nice warm day. You're going to have the air conditioning running. Well, you can literally go to that same air conditioning system, right, when the outside temperature is the same, and you can measure one day 12 degrees Celsius, another day 15 degrees Celsius, maybe another day 12 degrees of superheat, 15 degrees of superheat in Fahrenheit, let's say 16 degrees of superheat. So you have this large range of superheat, even though the outside temperature is the same. What is the difference is the amount of moisture in the air, humidity. In air conditioning, latent load plays a huge part in how much load variation you're going to have on an air conditioning system. And why is that? Well, most spaces, dwellings these days, right, unless you live in a tent or something, right, they have tons of air conditioning or tons of insulation. So at the same time, you also keep the temperature inside your, dwelling, your house, relatively the same temperature, 21, 22, 23 degrees Celsius, 72, 75 degrees Fahrenheit. You don't run your house down to 45 degrees like it's inside your fridge, right? So basically, the only thing that really changes in your house, other than a couple degrees of dry bulb, is the moisture. So if you have a humid day when the temperature outside is much higher than what it is inside, you have this huge load coming in of latent load. And this can be enormous compared to dry days. So your TXV and your evaporator, they don't really give a crap what load it is, whether it's latent or sensible. They just see it as load. So if you have this huge amount of humidity, right, your sensing bulb is going to realize that you're running out of a refrigerant quicker in your evaporator because you're trying to get rid of all this water in the air, and the TXV will throttle wide open. So in air conditioning systems, you can see this huge swing in superheat based on just the amount of moisture in the air. So,
Jamie,
anywhere from 10, 12, 15 degrees for AC down to maybe, 5, 7, 9 degrees Fahrenheit for low temp refrigeration.
Thank you, Jamie. We have a lot of questions coming in, so
I better keep it brief. I'm sorry. Okay.
But I think it's great, and a great explanation. Just for clarification, if it happens that we're not capable or does not have time enough to answer all the questions, we'll try to post answers afterwards. And also, by the way, you will be able to find this webcast recorded after we're done in about 3/4 of an hour, something like that. So please, if you don't get your question answered, then have a look later on. We'll try to do it as much as possible. Jamie, we have a question now about subcooling. It's from Ishan Sharma. He's asking why excess amount subcooling in refrigeration system degrade the system efficiency.
Okay. The quick answer to that is subcooling is reflective of a couple of things. Number one, your refrigerant charge, and number two, the load on the system. In other words, how high is your condensing pressure and temperature compared to the outside air, specifically with TXVs. So with a TXV system, which is kind of where we mostly focus on subcooling, that in electronic expansion valves, if you have a high level of subcooling, it can indicate, and this is occurring in the condenser, by the way, if this occurs in the condenser, not anywhere else. If you have an excessive amount of subcooling in the condenser, that indicates that you have a very large temperature difference between the condensing temperature, right, the saturation temperature of the refrigerant in the condenser, and the outside air, or whatever medium you're using to cool. So as you add refrigerant to a system when you're charging it, you'll notice that the condensing temperature and pressure continue to rise. And the temperature difference between the condenser and the outside air will continue to increase. And this temperature differential between the air and the refrigerant is the basis for subcooling, okay? Essentially, with a TXV or an electronic expansion valve, the subcooling on a system is a reflective of how much charge you have. So if you overcharge a system, you will end up with a greater subcooling value than what is often recommended by the manufacturers. So if you go to a charging chart for a, let's just take an air conditioning system, they recommend a specific value of subcooling based on your indoor wet bulb temperature, okay, which is indicative of, once again, how much humidity is inside, as well as the outside ambient temperature in dry bulb. So as the ambient temperature goes up outside, along with, say, an increase in wet bulb temperature inside, the amount of subcooling that you aim for with your refrigerant charge increases. But if you charge above that value that is recommended, your subcooling will increase. Well, subcooling is a benefit to the system because it reduces flash gas. However, the increase in pressure difference between the high and low side that you create when you overcharge overcomes whatever gain you get from additional subcooling. So the COP, the coefficient of performance, or the efficiency of the system, goes down once you increase your refrigerant charge above what is recommended. And this is also, once again, a danger to the system because now you have more refrigerant than you really can handle in the system. It's got nowhere to go. So if you charge the system on a relatively cool day and you overcharge it, if the temperature outside increases, a few weeks later, now you can be in a dangerously overcharged situation where the high side pressures are much higher than what they're designed for. And this can drastically shorten the life of the system and burn up a lot of energy that you normally wouldn't use. So high subcooling is generally detrimental when it's caused by an overcharged situation, or it's caused by lack of condenser heat rejection. So if you have air blockage in your condenser, if your condenser looks like it's wearing a sweater because there's so much, debris stuck to it, or there's a hedge growing around it so you can't even see it, right? This will hit your airflow, which will drive your condensing temperature and pressure up. This will also increase your subcooling. So subcooling then is an indication of poor heat rejection on the condenser side. And it's a great indication of going and having a look. Just look at the condenser outside and see what is going on. A lot of times it's visibly obvious if there is a problem. I hope that answers your question.
I'm sure it does. Jamie, we've got quite an interesting question here, actually, and we may actually have to sort of divert a bit from you could say the core theme. There's a question here from Masa Ibrahimi. Is there a difference in dry expansion and flooded evaporator? And I presume it has to do with superheating.
Mm-hmm. Yes, there's a lot of differences, and we'll focus on the superheat side. In a flooded system, pick a container of refrigerant. All right, and you have that container full of refrigerant, except for a little bit on top where there's vapor. And what you're doing is you're pouring refrigerant into that container on one side, right? And you're letting any excess liquid, if it gets above a certain level, flow out the other side and go back to your receiver. And on top, you're pulling vapor out of that container. That essentially is a flooded evaporator. In other words, the evaporator is pretty much full of refrigerant, and the vapor that you're pulling out of your evaporator is saturated. There is no superheat whatsoever because there's no circuitry to produce that superheat. So a lot of times, these flooded evaporators, in a system that we use, a TX valve, a dry expansion system, generally speaking, if the load is constant, you're putting in, let's say, a pound of refrigerant, and the load on the evaporator requires you to evaporate a pound of refrigerant, and it's relatively constant. In a flooded evaporator, if you had, X amount of load, instead of putting X amount of refrigerant in there, you're putting 2-3X worth of refrigerant into the evaporator, often 2-3 times as much as what's necessary to meet the load. And this seems bizarre, but really what you're doing is you're limiting the temperature rise in the evaporator to pretty much zero, regarding superheat. And this limits the, this limits the amount of superheat to zero going to your compressor. So if you have an ammonia system, So you don't want any superheat coming to that compressor, because ammonia is kind of like R22. Because of the isentropic curve or whatever of the refrigerant, your discharge temperature is very high for a given compression ratio. So you want your superheat to be pretty much zero at a ammonia compressor to limit that discharge temperature. But also efficiency is key here. So by pumping it, as much refrigerant as you can until it costs too much money to pump more, that is your sweet spot, because you're really trying to keep that evaporator temperature as low as possible. And by evaporator temperature, I'm talking average evaporator temperature. So if you take an average evaporator temperature, you also have to include the superheated circuits as well. And because superheat is higher than saturation, this pushes your average evaporator temperature up. So by keeping the evaporator temperature low, right, you literally can raise your evaporator pressure and temperature, because your average evaporator temperature is lower. So if you can raise your evaporator saturation temperature by 2, 3, 4 degrees, this brings it closer to the compressor pressure and temperature, and this reduces your compression ratio, and this increases your efficiency. So that's the key to a flooded system. You protect the compressor because there is this baffling and everything else that stops you from sucking liquid out of the evaporator at the top. You're only drawing this saturated vapor. It's wet vapor, but there's really no liquid into it. Whereas with a dry expansion, you literally let the liquid run out in the evaporator. You let the remaining vapor warm up in a circuit, and then you draw that dry superheated vapor out of the evaporator, and away you go with it. You try and limit it, but there absolutely has to be superheat with these types of systems, with a dry expansion system, because you're using a TXV.
Yeah. Great answer. We have another question from Abjahid Sinhe. If we have a perfect evaporation, if we have a perfect evaporator, and I think also perfect superheat, if the pipe run is too long, it will hurt the compressor winding. Should we look at the compressor superheat or evaporator superheat?
Yeah, that's a good question. The evaporator superheat is not the problem. If your evaporator superheat is where it's supposed to be, then you don't want to adjust that, okay? Because if you adjust it too low, then you have a chance of going below what we call the minimum stable superheat, and that's another conversation, which maybe get to in a second.
Yeah.
But what's happening is you are picking up unwanted superheat in your suction line. And this generally means your suction line is not insulated, or it's not insulated enough. So if you happen to have that suction line running through an untreated space, let's say that space is 25, 30, 35 degrees Celsius, 80, 90, 100 degrees Fahrenheit, you're going to pick up a lot of superheat in that suction line. Hence why, if it's not insulated. So that's why you want to insulate it. Because once again, high superheat at a compressor is detrimental, because it is making the compressor run hotter than what you want it to run, and your discharge temperatures can climb dangerously high. And once your discharge temperatures get above a certain point, you start to rapidly evaporate your oil. This lowers the viscosity of the oil, and it lowers the capability of that oil to maintain a safe film between moving parts. If you push the temperature of your discharge even higher, now you start to break down the oil. And this is when you get towards a situation, what we call a compressor burnout. So you absolutely 100% want to insulate that suction line. That is really the only way you can deal with this type of thing without having some kind of, liquid injection or something like that into the suction line, which you want to avoid at all costs unless you have to. All right. So insulate that suction line. Make sure there are no gaps. Make sure there's no place for you to pick up extra heat in that long suction line run. Excellent question, by the way.
Yeah, thanks. Raji Kumar Shinde has a question: how to select a compressor which will replace another compressor? I think it's a renewal of a compressor, if I may.
Okay, so a replacement. Okay.
Yeah.
That's a good one. Okay, first of all, if you're replacing a compressor that failed, first thing, absolutely 100%, first thing you have to do is figure out, why did that compressor fail? Compressors don't just up and die of shame or anything like that, right? They die for a reason. Generally, they are either overheated or got flooded. All right. Now, you may say, oh, well, what about voltage and everything else? Well, again, they cause a compressor to overheat, right? They cause a compressor to become flooded. There's all these external reasons of why these compressors either overheat or get flooded. But you need to find that core problem. Now, this can be hard because the compressor that you're replacing is already dead. Here's how to start. First thing you want to do is make sure that the replacement compressor is the right one. Now, here's the risk. You may go by the compressor that's already in there, but if the system is older and you don't know who's worked on this system before you, how do you know the compressor in there is the right one to begin with? Maybe the guy just put whatever compressor he happened to have on the truck at the time, and it was a close enough match, at least that's what they thought, but it turns out it was either too big, too small, didn't have the right voltage range. You would be surprised the number of times this happens. All right. So never assume what's in there is the right one until you verify with the nameplate on the unit. If the unit says 34,000 BTUs an hour or so many kilowatts or whatever it happens to be with a specific voltage, right, and all these other things, make sure your compressor matches that. All right. And then while you're at it, check your TXV capacity as well, and make sure that your thermal expansion valve is also rated for the same capacity at the evaporator temperature you're operating at, whether it's a freezer, a cooler, or an air conditioning system, whatever. And also make sure the refrigerants match as well, that somebody just didn't dump some weird drop-in refrigerant that really wasn't supposed to be in there. What you're really trying to do is eliminate as many possible causes for why that compressor failed before you push the button and start the system and walk away. So once you have verified you have the compressor based on refrigerant, capacity, voltage, oil, things like that, then once you do your startup, right, the first thing you want to do is measure the amount of refrigerant that you take out of the system. Okay. So, before you pull the old compressor out, recover that refrigerant and weigh how much is there. Why? Because if the charge on the system is supposed to be 1.5 kilograms and you pull 900 grams out of the system, well, maybe that's why the compressor failed, right? Because it's undercharged. Yeah. Very few systems are undercharged by people installing them. The vast majority are overcharged. So if you're pulling out a lot less refrigerant than supposed to be in there, that's probably a good place, a good time to start looking for leaks. All right. And check the system for leaks. If it's 1.5 kilogram charge and you pull 2.5 kilograms out, well, that's not a good thing either. Okay. Even if it's not the reason the compressor died, you are still going to make that system operate 100% better if you actually charge according to what's supposed to be in there. Yeah. Okay. Whatever it says on the nameplate. So again, you're trying to eliminate all the possible causes for this compressor to fail during the replacement and startup procedures. Measure your voltage, check your start capacitors and relays, make sure everything starts quickly. Look at your piping runs to make sure that nothing is going to hold oil up. All this stuff is very important to do when you're replacing that compressor.
Yeah.
Probably more than you wanted, but there it is.
Yeah, great. Okay, actually, we have a question here from Avis Sayed, which sort of it's actually a question that goes with what you just explained about charging. His question is: liquid refrigerants charging is a non-standard practice.
No, I wouldn't say that.
Okay, me either. But I have seen a lot of tech is charging the liquid refrigerant after evacuation. What is your suggestions for them?
Okay. Yeah. Really, a lot of systems with the new refrigerants, they are what we call blends. In other words, you take this refrigerant, and this refrigerant, and you mix them together in certain ratios until you have the resulting properties that you want. And these refrigerants don't act like a single blend. It's not like the old R12 or, you know, R22 or these other single refrigerants. Generally speaking, they're a mixture. And these have to be charged by liquid, because if you charge by vapor, some components of that blend, one of the 3 refrigerants they put together to make it, is going to boil quicker than the other ones. So if you draw the vapor off, when you first start, you're going to get more refrigerant of one kind than the other. So what you're actually putting in the system is not what you want. That is not the refrigerant that says on the jug. It's only one part of it. So by these, you need to charge liquid. And to charge liquid, generally speaking, you want to put as much into the high side as you can. If you can get the whole thing in there, great, right? And the rest, if you got to put it in to the low side of the compressor somewhere, if there's an accumulator, put it upstream and throttle it through your gauges or your charging station so that it actually flashes going through. But you literally are drawing a liquid out of the container, out of the refrigerant jug. You absolutely have to charge these with liquid. I know it seems kind of counterintuitive, but unfortunately that has been a reality for the last, 30 years or so.
Thank you, James. We have a question from Mohammed Malik.
Okay.
I hear internal superheat, external superheat in aircon, and compressor superheat. What's the difference between the 3 superheats?
Internal superheat is generally what's picked up inside the evaporator. We call this useful superheat because it's actually part of the net refrigeration effect. It's part of the heat that's being absorbed by the refrigerant. So it's actually doing useful work in the evaporator. External superheat, a lot of times we refer generally as superheat that's picked up in the suction line. So we had a question before about that. So superheat that's picked up in the suction line that is unwanted and it's not doing any useful work, we call this external superheat. Both of these superheats are combined, and you measure this at the compressor. So compressor superheat, all right, a lot of times is called saturated superheat, all right? And it sounds stupid, compressor saturated, but it basically, the reason we do this is this. The suction pressure is not the same pressure as the outlet of the evaporator. Now, most of the times you want to keep this as close as possible. But if you have long suction line runs, a lot of times you can have your saturation temperature at your compressor can be 2 or 3 degrees lower than what it is at the evaporator. So believe it or not, even if you didn't pick up any superheat in the suction line, if you're going from, 8 Kelvin of superheat at the evaporator outlet and you let the pressure drop in your suction line an equivalent of 2 Kelvin, even if you haven't picked up any extra superheat, because your saturation temperature is now 2 degrees lower, you've literally picked up an additional 2 degrees of Kelvin of superheat. So you're going to measure 10 Kelvin at the compressor. So if you combine this with superheat you do pick up in the suction line, this is going to add up substantially. So a lot of times you will see manufacturers recommend superheat at the compressor suction being substantially higher than what you would see at the evaporator. So for air conditioning systems, a lot of times you will see recommended suction superheat at levels of 25 and 30 degrees Fahrenheit, 10, 15, Rankine easily, or 10 or 15 degrees Kelvin easy at the suction side of the compressor. Whereas you might have a value 5 or even 10 degrees lower than that at the evaporator outlet. Because again, the amount of superheat you want the compressor increases the higher your evaporator temperatures. So it's going to be very minimal for, low temp applications, but the amount of superheat at the compressor to ensure it's dry is going to be a lot higher for air conditioning. That's why you see those 3 different types of superheat.
Great, thanks. Jamie, I think I would like to take the opportunity to do some well, if I say promotion, it's not right, but anyway, some of you guys may have seen the refrigerant slider from Danfoss.
I love this thing, man. This is awesome.
Yeah, there is a new addition, and you can probably not see it here now, but it's under Tools, you'll find a TXV Superheat Tuner. And that's very interesting for the next question, actually, which is from Vishaka Jawale. How to decide subcooling efficiency, I guess it is.
Sufficient, okay. All right. Do you want me to answer that now?
Yes, please.
Okay. As a manufacturer of components that go into other people's equipment, you know, we sell to people that actually manufacture equipment. We generally state that manufacturers will tell you how much subcooling you need. And this is very important for things like air conditioning, in that you actually charge to subcooling. All right. So if you're taking it from a charging standpoint, follow a manufacturer's recommendation. But in reality, especially in refrigeration and things like that, the amount of subcooling you're going to have is going to depend on things like, do you have a receiver? You know, how full is the receiver? In supermarket systems, for example, you know, with multiple evaporators, you know, maybe this is going too far, but if a lot of your evaporators are loaded, you're going to have a very high turnover rate in the condenser. In other words, you're going to have a lot of refrigerant coming in the condenser and a lot of refrigerant coming out of the condenser. Whereas if, say, at nighttime, you don't have any load at all, hardly, the refrigerant's going to sit in the receiver for a long period of time before it goes anywhere. Well, if it sits in the receiver, you're going to lose subcooling. So a lot of times you'll see these supermarkets, they might have 2-3 degrees of Kelvin of subcooling. Sorry, 2 or 3 degrees of Kelvin of subcooling. Whereas at higher loads, they might have 4 or 5 degrees of Kelvin, if you're lucky. Air conditioning is kind of a different story. With air conditioning systems, a lot of times you're aiming for maybe 8, 9, up to 11 or 12 degrees, you know, Fahrenheit of subcooling, you know, 5, 6, 7 Kelvin of subcooling in a lot of these air conditioning systems. So there really is no definitive answer. All I can say is if you're charging a system that has no indication of what the subcooling is supposed to be, and it's a single evaporator system, you know, with a condensing unit, and you have a TXV and maybe there's a receiver on it, you know, charge to, you know, anywhere from 4 to 6 degrees Kelvin, you know, 7, 8 degrees of Fahrenheit subcooling. That's going to be more than enough to overcome whatever restrictions or pressure loss is going to be in the liquid line. But always keep an eye on your condensing temperatures, right? You know, your condensing temperature split, if your condenser is, you know, relatively efficient, should be anywhere from 15 to 20 degrees Fahrenheit between, you know, the refrigerant and the air temperature. If you get much above that, then that usually tells you that you're, you know, a little bit overcharged. You'll see your subcooling values very high. But again, this is more of a practice thing, understanding the equipment you work on. So it's just not an answer I can say, oh, look for 4 degrees, look for 6 degrees, look for 8 degrees. It's like superheat. There really is no fixed answer, unfortunately, that I can give you. I wish there was, but there isn't. Oh, if you want to know really if you have enough subcooling in the end, if you have no flash gas at your metering device and you have a solid column of liquid, you have enough subcooling, right? As long as you have subcooling at the subcooled liquid at your metering devices, you're good to go, right? That's probably the bottom line, the easiest answer now that I've seen it.
Great. Yeah, another question. Avis Sayed, if a system have more superheat ambient, also high, what's the impact effect on the compressor?
I like this question. This is kind of a double negative. We already mentioned that the vapor cools the compressor in the suction line. So if your superheat is high, you have a harder time cooling the compressor. If your outside ambient temperature is high, it also means that your condensing temperature has to be high as well, because the refrigerant, your condensing temperature, has to be warmer than the outside air in order to reject heat. That's just the laws of thermodynamics. So if you have a high temperature ambient day where it's 32, 35 degrees Celsius outside, or warmer, and you have way too much superheat in your evaporator or your suction line, this means you are not only not cooling the compressor properly, but your compressor is generating even more heat because it has to do more work to overcome that larger compression ratio between the evaporator and the outside air. So it's like a double whammy. In other words, you're having a harder time cooling the compressor, but at the same time, the compressor is also producing even more heat because it has to work harder. Generally speaking, this is a recipe for a compressor that has a short lifespan. And, this is something that occurs generally before you see a compressor failure or a system with very poor cooling performance. All these kinds of things show up, and none of them are any good. They're all a negative. That's generally the result of that.
Oh, okay. Bernardo Ramalho, I think that's probably it's pronounced. How should we verify the correct superheat in a dry expansion, low temperature line when I have long lines and pressure drop?
Okay, this is again kind of what we went by. If you look at the compressor manufacturer or the manufacturer of the equipment, they will specify what that temperature should be. So if you're talking about, it says I take a DX low temperature line, that generally means you're talking, a freezer. If you're looking at Fahrenheit or Rankine or whatever you want to use, 15, 20 degrees maybe maximum if it's insulated, maybe 25. If you're talking about a higher temperature, it can be more. But generally speaking, the manufacturer will recommend a specific amount of superheat at the compressor. Okay. And I think it's called a saturated suction superheat value, SSH or whatever. So if at all possible, go to that manufacturer's recommendation because they know their compressors, and every compressor has a different value that it will tolerate based on how it's set up. But again, once you have a low temp compressor, you generally want to try and limit those as much as you can. All right. But again, go by what the manufacturer states, okay, if at all possible. And to be honest with you, insulate the suction line. If the suction line is insulated, there's really nothing else you can do if your evaporator superheat is fine. Okay. There's nothing else you can do really. So
true.
I like this question.
William Savre, what is the recommended subcooling value for racks systems? And what's the purpose of additional subcooling economizer on certain systems?
Yes, well, you answered that question when you wrote economizer, because you heard me talk about the negative effect of subcooling or using subcooling as an indication of something that's not right, and that's overcharging. All right, because in a condenser, you can only pick up so much subcooling because you want the majority of your condenser to reject heat by condensing vapor to a liquid. This is called latent heat. And this is by far where the evaporator condenser does most of their work. The majority of heat is absorbed in the evaporator by turning liquid to vapor. And the majority of heat is rejected from the condenser by changing vapor to a liquid. That's how it works. So you don't want your condenser full of liquid because this will actually reduce the capacity of your condenser. Okay, and we actually use this during times when it's really cold outside and we're worried our condensing temperature is too low. So we flood the condenser. But you don't want to do this when it's hot out. So if you can't add additional subcooling in the condenser, where do you add it? Well, it's just like I talked about adding superheat, right, to a vapor coming out of your kettle. You capture that vapor and you heat it up some more. Well, what we do with a subcooler is we capture that liquid after it leaves the condenser and we actually cool it down some more. So we can either run it through a loop outside if it's a cold day and actually subcool it even more, or we can use a subcooler, which essentially uses like a TXV or something like that, and runs it through a heat exchanger and cools down the liquid refrigerant even more. The reason we do this is very straightforward. And this is where understanding the pressure enthalpy diagram of the refrigerant comes in handy. The condenser is, if you think of your refrigerant as a bucket that can hold so much water, in this case, it holds so much heat. It's a bucket that holds heat. In the evaporator, you're filling that bucket up. Okay, you're trying to fill it up with as much heat as possible. But the amount of heat you can put in the bucket determines how empty it already is. If it's completely empty, you can basically have that entire volume of the bucket you can use to put heat in. But if your bucket's already, let's say, a third full, then you can only put 2/3 of the heat in the bucket that you normally could if it was empty. Now, when you reject heat in the condenser and your liquid leaves, it still has not gotten rid of all the heat that it possibly can. The only time you did that was if you cooled the liquid leaving the condenser, if you cooled it to the same temperature as your evaporator. But we don't do that, right? We might condense at, let's say, 35 degrees Celsius, and we leave the condenser at 32 degrees Celsius. So we have 3 degrees of subcooling, or 4 degrees, whatever you want to make it. But our evaporator is running at, 5 degrees Celsius. So we would have to cool that liquid in the condenser down to 5 degrees Celsius before we literally emptied that bucket completely. Okay? Because in the evaporator, when that liquid goes through the metering device, all that extra heat that's in the refrigerant, because it's not the same temperature, the liquid is not the same temperature that the evaporator is at, that extra heat has to go somewhere, right? So it literally goes in creating flash gas. So you have this flash gas being formed out of your metering device. And so you don't get 100% liquid coming out of your metering device. You get maybe 50, 60, maybe 70% if you're lucky, liquid. The rest is vapor. And unfortunately, that vapor does nothing in the evaporator as far as absorbing heat. It just goes along for the ride until the last little bit when you superheat it. So when you subcool a liquid outside of the condenser, you are literally taking out more heat. You are emptying that bucket even more so that when it goes into the evaporator, you have less flash gas and you have more liquid. This means that every pound or every kilogram of refrigerant can absorb even more heat because this bucket is a lot more empty than it would have normally been. So this means that you don't have to pump as much refrigerant. So if before you had to pump 2 pounds a minute of refrigerant, if you cool that the liquid refrigerant down in a subcooling, instead of 2 pounds of refrigerant a minute, maybe you only have to pump 1.6 pounds or 1.5 pounds. So this means your compressor is doing a heck of a lot less work for the same amount of refrigeration effect in the evaporator. And this, of course, drives your efficiency and your COP up and saves a ton of energy. So that's what a subcooling circuit does.
Perfect. Thank you. Mohammed Malik has a question about zeotropic refrigerant. How is superheat calculated with a zeotropic refrigerant?
Okay, you're talking about the ones with glide then. This is kind of a tough question to just answer without diagrams and things like that. But generally, you have your dew and bubble point. And what you want to do is you want to use the value that's recommended by the manufacturer in order to calculate it. And this takes into account glide. And unfortunately, off the top of my head, I am stumped right now because I can't remember which one to actually use. And I should know this, but it's been such a long time since somebody asked this question. But essentially what you're looking at is you want to look at what the actual saturation temperature is of the refrigerant when it's leaving after all the parts of the blend have evaporated. And that's really what you want to determine your amount of superheat on. So again, you really have to look at what the value the manufacturer wants you to give. And unfortunately, I apologize, I cannot give you a better answer. I have seen some amazing explanations of this online in videos, so I highly suggest you look it up. But again, off the top of my head, I just find it very difficult to answer this question. I'm sorry.
We have, I was just trying to see if I could find that link but on our webpage somewhere, sorry, but to be so unprecise, but we have actually a paper on zeotropics and the adjustment of superheat in that context. So
yeah,
Mohammed,
I'm embarrassed to actually not be able to answer this because, again, shame on me, but it's just completely slipped my mind, man.
yeah, but it's a tough subject. But Mohammed Malik, try look it up on our webpage, stanford.com. You should be able to find it somewhere. It's yeah, try it out. We have a question from
yes.
that's a Dang Hu.
Yeah.
I'm not sure about the first name, or is that a family name? In some selection of software of compressor manufacturers, you have two superheat items, useful and non-useful superheat. Could you please talk about that? I think we've touched on that. So maybe
yeah, useful superheat is what occurs inside the evaporator. Non-useful superheat is what happens in the suction line. We call it useful superheat in the evaporator because it is actually contributing to the net refrigeration effect. It is actually doing work for you by absorbing heat that you want to remove. Whereas in the suction line, all you're doing is cooling the outdoors, which is not something we really want to do, at least in this situation.
Yeah. Any more questions? Yeah, here we go. That's a good one. Roland Obiera. Yeah. On a Danfoss variable speeds compressor and a scroll compressor with low load, it's normally if the compressor sweats. Is it normal if the compressor sweats, or could it be damage on the compressor? What could be done?
Good question. Yes, it is normal for a compressor to sweat, as long as it's not sweating around the discharge line. If you look at the bottom of the compressor, all that's telling you if a compressor sweats is if it's below the dew point temperature of the air. In other words, if the air is humid, the temperature at which moisture will condense against a surface is actually quite high. So if the compressor sump temperature, and by all means it usually is, if it's below the dew point temperature of the air, it will sweat. That's normal. It's the same as a suction line. You're going to have sweat around it. However, if the head of the compressor and around the discharge line is sweating and it's cold or whatever, now that's a problem because that means you're getting liquid back to the compressor and there's all kinds of other issues. So with low load, once again, generally speaking, your evaporator temperature is going to drop lower, which means your saturation temperature is going to be low and your superheat is going to be low because of your low load, right? Especially if you have an electronic expansion valve, it's going to try and maintain minimum superheat. So the returning gas temperature to the compressor is also going to be low. So taken together, that is absolutely not uncommon for the compressor to sweat. So that in itself is not something to be concerned about. As long as there's no other issues, like you're not losing compressors every second week or something like that.
Yeah. We have quite an interesting question here from Mr. Conrad. Sometimes the oil doesn't return to the compressor. It stays in the evaporator. Does the superheat affect that?
Yeah. You know, I heard a saying one time come from one of my instructors back when I was in college. He goes, you know, I've seen some refrigerant piping that's so bad that your oil actually turns into a electrical question because you're absolutely shocked when it does come back. Right. And it's a bad joke, but it gets the point across. Under low loads, when your amount of refrigerant through the evaporator is lower, the velocity of the refrigerant is actually lower as well. So is your mass flow. So a lot of times this will leave a little more oil in the evaporator than there should be. Generally speaking, this is swept back up again once the load increases. But if your evaporator has some design issues, or if you have too much oil in the system because somebody either took a compressor out and didn't account for the amount of oil already in the system when they put a new one in, or whatever, you can end up with excess oil. This affects superheat in the sense that it reduces the heat transfer between the refrigerant and the walls of your evaporator. It does the same thing in the condenser. Okay. So what ends up happening is if you normally had a 5 degrees Celsius saturation temperature. If you have too much oil, you might have to run a 3 or 2 degrees Celsius evaporator temperature for the same effect. Okay. What ends up happening is this can essentially change the values of your superheat slightly. And it's essentially acts like insulating the evaporator. It's no different than if you happen to have ice on your evaporator. It's going to drive your saturation temperature down. A lot of times it will decrease your superheat because you have a harder time getting the load to getting the refrigerant to pick up load and absorb heat. So really, it's a situation where you're interfering with heat absorption in the evaporator. That can often drive your superheat down, but eventually the temperature will continue to drop in the evaporator until you meet that load, right? The system will become less efficient, but it really shouldn't affect your superheat by a huge amount, at least off the top of my head, at least from my own experience back doing service. Now, having said that, if you have a ton of oil in your suction line where your sensing bulb is, this can cause a problem because the oil going by your sensing bulb interferes with the actual temperature of the refrigerant. Why? Because your oil is not the same temperature as your suction gas. You may think it is, but it's not. It doesn't become superheat. It doesn't rise in temperature as quickly. So you can have superheated vapor going by the pipe where your sensing bulb is sitting, and suddenly you get a bunch of oil go by there. Well, that may lower your pipe temperature 2 or 3 degrees. Well, this tells you that there is much less superheat now in the evaporator than there was. That's what the sensing bulb thinks, because now it's being cooled down. So this causes your TXV to throttle closed. And once that oil passes and the refrigerant vapor returns, this warms your sensing bulb back up again, and bingo, the TXV opens back up again. So the main issue here is an unstable TXV hunting and an unstable or unstable pressure and temperature in your evaporator. That's a lot of times what you'll see.
Thanks, Jamie. The last question, because we are
we out of time already? Oh man.
Yeah, we're getting there at least, and also getting over the time actually. But we have a question here from Rudy, which I think is quite good. I've seen many technicians charge a freezer or cold room system by using the sight glass on the liquid line as an indication of a full charge. Is that necessary? Is that necessarily the correct way to determine a full charge?
Really, what the full sight glass does with most refrigerants is it tells you that you have a full column of liquid. Now, the issue here is, what is your load on your evaporator or evaporators? If your load is high, right, and you charge to a high evaporator load, you may be okay, because under high evaporator loads, you have more refrigerant in your evaporator, right? So if you have a fixed load or fixed refrigerant charge and you have more refrigerant in your evaporator, it means you have less refrigerant everywhere else in the system, okay, which affects subcooling and everything else. So if you're going to err on the side of caution and you charge according to a full sight glass when your load is really high, as long as you got a receiver that can hold that refrigerant, all right, when the load is low, then you're probably going to be okay, because under low load, you have less refrigerant in your evaporator, which means it has to go somewhere else. So unless you want to fill your condenser up with refrigerant, right, it has to have some place to be stored. Now, with some of the blended refrigerants, it can be quite difficult to get a full sight glass, because you're still going to get a few bubbles here and there just because of the different types of refrigerant blends in there. So a lot of times what you want to go by is subcooling rather than a full sight glass. I don't want to tell people not to charge to a full sight glass, because there are times when it can be done. But at the same time, take a look at your subcooling and take a look at the temperature spread between your refrigerant and the outside air. Generally speaking, you want to compare those two, right? If the condenser is designed for the 15 or 20 degree spread between the condensing temperature and the outside air, and you're within that range, chances are you're doing all right, okay? As well as you have sufficient subcooling, 6, 7, 8 degrees of subcooling or whatever the manufacturer of the walk-in box, whatever else recommends. You generally can't go wrong there. But charging to a sight glass works all the time, except when it doesn't. And it's that time when it doesn't, that's when you're going to be in problem, because you're dealing with specific blends that will show, you know, the odd bubble in the sight glass, even though you actually have more than enough refrigerant in the system.
Yeah, yeah, true. Jamie, thank you so much.
Thank you.
Just to mention it again, this will, or it has been recorded, this live stream here, and we have quite a few questions actually that we haven't been able to answer today.
Yeah, it's too bad we couldn't. Yeah, it's too bad. It went too quick, man. Oh, wow.
But please look back or come back in a few hours, maybe a few days, and we'll have written answers for all of you on all of your questions in the comments part of the recording, which I presume will be on YouTube. Come back and have a look, see if there are any answers to your questions there.
Yeah.
Yeah. Thank you so much, Jamie. You have any last words to our audience?
Last words. Yeah, no, it's a never-ending topic, because again, unfortunately, there are some questions that are going to be very specific to certain situations, and it's difficult for us to answer because, again, you know, I'm not there. I'm not looking at the equipment. I'm not looking at the shape it's in. I'm not looking at, you know, the capacity balance between the evaporator and the condenser. There's all these things. So if you think, you know, why doesn't he just give an answer for a particular value of subcooling or superheat? It's because many times there isn't a particular value of subcooling or superheat. It's dangerous to go by a rule of thumb and apply it across the board. You might be okay 80% of the time, 90% of the time, but just keep in mind that, you know, when we have a lot of compressor failures, if you look at most of the warranty fit compressors that fail and things like that, they fail for a reason. And every time they fail for a reason, it means that something wasn't done right. And a lot of times you can do something that's right, you know, 9 out of 10 times, but you do it that one time it's not. That's when it's a problem. So that's why I'm hesitant sometimes just to throw out a value for something, because to be honest with you, there is no perfect value unless it is something the manufacturer recommends. And when a manufacturer recommends it, it means they've tested it in their labs. They've gone through stress tests. They've gone through all kinds of stuff to determine that when you use X component and Y component and put them together, right, we know it's going to behave a certain way. And in doing that, this is the value of superheat or subcooling you should charge to or look for. That's about it. Thanks for coming out, people. Thanks for the amazing questions and taking the time to put them in. I really appreciate it.
Thank you, all of you guys. It's been a pleasure. And Jamie, thank you so much for your great answer.
Anytime. This is a lot of fun. I could keep doing this all the time. It saves me from having to do all my real work.
Okay, but thank you so much, and have a nice rest of the day, evening, morning.
Yeah, for a lot of you guys, evening. For guys like me, morning.
Yeah,
so.
Good. Okay, bye-bye.
Bye. Take care, people.